So today I'm going to talk about unitary representations, and I'm going to try to cover a lot of things. I'm an expert in none. I learned recently the perfect saying for that, so I'm going to teach my grandma to suck eggs. So I think this is how it works. So a little reminder here is the whole point of thinking about unitary representations is that I was interested in isometric action on spheres, and isometric action on spheres are in one-to-one correspondence with orthogonal representations of this group. And remember that from this representation, we got a harmonic map by quote-unquote harmonic map theory. And in order to try to understand the limiting behavior of those psi j when j becomes large, so this dimension is going to go to infinity, we better have to understand the limit or the asymptotic behavior of those actions. So those actions, we would like to take them, for example, at random, and so the dynamics of those actions are going to be very complicated a priori, and we're going to see how to describe this asymptotic behavior. All right. So unitary representations, I've heard that you've seen a lot about unitary representations with Roman Sauer and Barbara Shapira, so I'm going to be a little bit fast here. I'm going to consider a finitely generated group, and maybe sometimes, so when I consider let's just consider a finitely generated group. So we're interested in morphism from this group to the unitary group of some Hilbert space. So let me be clear here that I'm going to consider complex Hilbert spaces, and they're all going to be separable, just to avoid any technicalities. And U is the space of unitary matrices or unitary transformations that are onto. By the way, a good source for a lot of what I'm going to talk about is the book on property T by Becca de la Harpe and Valette. Oops. Property T, yeah. So let me give you right away the most canonical example. If you give me any group, you can define the regular representation. So what is this? Well, let's consider the set of L2 functions defined on gamma that are complex valued. So the regular representation is going to do the following. If you give me gamma and x in the group, and any L2 function on the group, I'm writing way too big. OK, so up. So what is the action of gamma on F? It's going to be that. So this is called the left regular representation. And it's going to be a very important representation for us because it's going to be the good description of the limits of those random representations. So I remind you that there's this notion of irreducibility. I'm not going to write down the definition, but being irreducible means that any invariant subspace of your Hilbert space, so invariant by the group action, is either trivial or the whole space. Also, sometimes I'm going to use the following notion of direct sum. So what this means is that it's the usual thing, right? You take the direct sum of the Hilbert spaces for row 1 and row 2. And so row 1 and row 2 are going to act on each factor, or on each terms. And so that induces an action on the whole space. I'm also going to look at the generalization of this construction, which is when you're allowed to take an infinite direct sum. So here, what you do is you take an infinite direct sum. You need to be a little bit careful, take the closure to get the Hilbert space, etc. So everything is explained in that book. And I want to remind you what strongly equivalent means. So what that means is that there is a fixed unitary transformation such that up to conjugation by this transformation, the two representations are exactly equal. All right, so this is a standard notion of equivalence for representations. It means that up to change of coordinate, really you have exactly the same representation. The claim is that in infinite dimension, this notion of strong convergence, strong equivalence is way too strong. And the right notion of equivalence somehow is much weaker. It's called weak equivalence, and this is what I'm going to define in a moment. Let's see. So I'm going to define weak containments, denoted by this, and weak equivalence. That's usually denoted by this. So you give me two representations, pi and nu, with h and k two corresponding Hilbert spaces. Then you're going to say that pi is weakly contained in the other representation if the following happens. So I'm going to copy the definition, and I'm going to explain geometrically what's happening. So the definition is a little bit tedious to write, but there's a nice interpretation. Let's see, up. Up. All right. OK, so this is weak containment. So let's read it together. What it says is that for any given vector in the first Hilbert space, and for any epsilon, I can find a finite number of vectors in the second space k, such that if you compare those scalar products, they are almost the same. Geometrically, it means that so think of pi as an action of your group on H. So the action of your group on H can be approximated by the action of your group on the second space. This is what it means.
And that row is new, actually. That row is new.
Probably, yes. Yes. Thanks. Thanks. So maybe you need to take several vectors, but finitely many vectors. And if you take the sum of those matrix coefficients, you get something very similar. So by the way, those quantities are usually called matrix coefficients. And the next thing is, as you can guess, so if one is contained in the other, then you say that they're weakly equivalent. So being weakly equivalent means that you can approximate the action of one by the other and vice versa. I like to think of everything geometrically, and remember that this quantity basically gives you the distance, the geometric distance in H between the image of psi with the vector psi, up to taking the r cos or something. Right, so is there any question on this definition? It's going to be pretty important for us, so I'd like to have everyone on board.
Is there matrix coefficient interpretation of strongly equivalence? So to compare, like how?
Oh, yeah. Sorry. So if you have the same matrix coefficients, then it's strongly equivalent.
Okay.
If this is your remark. Let me write it down. So such things are called matrix coefficients, and so by the, maybe you've seen it, but by the GNS constructions, so if you give me all the matrix coefficients of your representation, that completely determines up to strong equivalence the representations. Okay? Yeah. And let me explain how we're going to use it. So if you have two representations, rho 1 and rho 2, on two different Hilbert spaces, H1 and H2, remember that I care about maps from a given surface to spheres that are going to be equivariant by actions. And what I'm going to say here is that whatever map that's equivariant for rho 1, I can approximate it nicely by another map, which is going to be equivalent by, with respect to rho 2. Remember that S tilde is this universal cover. So it's just a surface. And let's say rho 1 equivariant. So for any epsilon at least 0, strictly positive, for any such map psi 1, you can cook up another map. So here SH is the unit sphere in H. Such that the two maps are very close, at least at an intrinsic level. So up to rotation of the spheres. So, So quick reminder, E is the energy, so it's computed using the pullback metric. This little thing here is the fundamental domain in S tilde. So what I'm saying is that once you give me a map here, you can get another map there, equivalent for the other action, such that if you look at any given fundamental domain, the two energies are almost the same. Right. questions on this?
By some kind of boundary between the distance of the images, if you somehow normalize correctly?
So the two images are going to live in different spheres somehow. Yeah. But you can say, okay, maybe there's a isometry from the first Hilbert space to the second Hilbert space that brings the first image very close to the second image. And this is true. This is true. Okay, so as stated, this is not exactly true, and I want to amend that, which is that really what the definition is saying is that, and I'm just going to write it in little here, the definition here is saying that pi can be approximated by the infinite sum of nu, if you think about that, because you need to take this sum. And so I should have replaced here I should have replaced rho 2 by the direct sum, infinite direct sum of rho 2. But for us, let's forget about that. Okay? So weak equivalence means that, roughly speaking, one approximates the other. How do you check that in practice, say? How do you characterize this? And here's a theorem that I'm going to call norm characterization so that I can refer to it later. Norm characterization of weak equivalence. The following are equivalent. So the first thing is that they're weakly equivalent. And the second condition is that this inequality is true. And I'm going to explain what this means. Oh, yeah. Okay, so okay, let's change that to equal then. So weak containment is equivalent to this inequality, and weak equivalence is this. Thank you. So for those of you who are not familiar with those definitions, so here C gamma is just the finite complex linear combinations of elements in gamma. And once you have such an element, such a linear combination, this is well defined and is going to go from H1 to itself, right? So if you think of F as, for example, given by one element, of course it's well defined. You can take sums, and you can take scaling. So that's why it's well defined. Next, this notation means always, for me, operator norm. Right. So this is a pretty concrete way with which you can check that two representations are weakly equivalent. This is all I want to say about the general theory. So the next thing I'm going to talk about is the representation theory for PSL to R.
Sorry, is this tensing L2 of gamma?
L, is this what?
This is like C gamma tensing L2 of gamma. Oh, they're not different. Oh, it's different, sorry.
Yeah. So I'm going to be kind of opportunistic. I'm going to cherry pick results and definitions that are going to be useful to us. But fortunately, I think the results I cherry picked are very general and fundamental. OK, so for the representation theory of PSL2R, remember PSL2R, you can identify it with the isometric group, oriented isometric group of the hyperbolic plane. And you can ask, well, what are the representations, the unitary representations of this Lie group? Turns out if you look at irreducible representations, those are completely classifiable. And more general representations can be written as a kind of integral in terms of those irreducibles. And this classification is very, very classical and is due to at least those people. Bargmann. So if you're not an expert in this and you just want to have a quick overview of what's happening, you can take a look at the book of Lubotsky. On expanders, one of the books of Lubotsky on expanders. There's a chapter on that. So let me just say, I'm going to focus on one particular irreducible representation of PSL2R, but let me just say that irreducible unitary reps of PSL2R are completely classified, and they're organized in discrete and continuous families called the principal series. So this is a continuous family of representations. The complementary series and the discrete ones. And as I said, I want to focus on a special representations. So usually called rho zero, and it's part of the principal series. So I'm going to describe very explicitly what rho zero is with completely explicit formulas. So that's going to take maybe 5 to 10 minutes. I want to recall some notations. So for me, H is going to be the hyperbolic plane, two-dimensional hyperbolic plane. And I'm going to always fix a base point that I'm going to call little o. You can look at its boundary at infinity, so I'm not going to write down the infinity here. And I'm going to look at the L2 space on the boundary of the hyperbolic plane. So this boundary, once you fix this base point, this boundary is endowed with a natural round measure, a uniform measure. Think of it as a circle. And so this L2 space is well defined. So the unit sphere in this Hilbert space is going to be called SL2. Another thing I want to remind you, which is that given any point on the boundary, you have the Boozman function, a well-defined function. So if you've seen it, that's fine. If you're not too comfortable with it, just know that it's a renormalized distance function. So theta is at infinity, and x is a point in the hyperbolic plane. Okay. So PSL2R is the group of oriented isometries of H. So it also acts on the boundary. Up. And thanks to those actions, I'm going to now write down the formula for this special unitary representation. All right. So what is this representation? So for any gamma in PSL2R, for any function, and for any theta on the boundary, I need to tell you what this function is doing to theta, right? So what is this? It's simply this thing. So here B theta is the Boozman function. Little o, remember, is just a fixed forever base point on H. And that gives you a function of theta, which is going to be the image of f by gamma. Any question on this definition?
So just to be clear, the Boozman function is defined with respect
to O, to little o, yeah. Once you fix this O, it's well defined. Questions? So this is, think of it as a PSL2R action on some unit sphere, which is very explicit, and we're going to be extremely interested in one orbit of this action, the orbit of the constant function 1. So it's going to be the image of the hyperbolic plane by some map P. Here, 1 is the constant function 1 on the boundary, so that its L2 norm is 1. So that this orbit really lives in the unit sphere in L2. And I'm claiming that, well, this orbit is actually two-dimensional, and it's the image by some map P of the hyperbolic plane. So what is this map P? I'm always, whenever I have this Hilbert space, I'm always looking only at the Hilbert metric. So this is, by our definition of the representation, the orbit of 1.
Sorry, what is 1?
1 is the, let's say that you normalize your measure on the boundary, the circle, to be 1. And then, so 1 is just a constant function of 1. So you just take one particular function and you move it around by PSL2R. And so the image of this map is supposed to describe this orbit. So why is that useful to us, right? So I'm going to write down the lemma, and hopefully it's going to be more clear why this is useful. So let me take gamma here as the fundamental group of some closed surface S. So the surface is a Riemann surface, meaning that it has a unique hyperbolic conformal metric. And so gamma is naturally embedded in a certain way in PSL2R. Okay? And now what I want to consider is not a representation of PSL2R. Actually, I'm caring about representations of the discrete group pi1 of S. Up. I'm going to call this embedding I. So what is rho B? I define it as the composition of the embedding I with rho 0. So this is a well-defined unitary representation of gamma. So here's the lemma that's going to make all of this useful. I'm going to give it a name. The content of the lemma is going to justify its name. So the first thing is that rho B is, so it's irreducible, which is good to know. But also, rho B, important, this is the important point, it's weakly equivalent to the regular representation of pi1 of S. So even though it looks quite different from the regular representation, it's actually completely weakly equivalent. And the second point, the geometric point, is that this map that I just defined, if you think of it from H with a rescaled hyperbolic metric, to that unit sphere in L2 with the usual Hilbert metric, this is an isometric and minimal. This is and minimal embedding of your hyperbolic plane, rescaled hyperbolic plane. And moreover, it's equivariant with respect to rho B. So that's an amazing, from a geometric point of view, this embedding is an amazing embedding because it's not only isometric, but also a minimal embedding. And I remind you that being a minimal embedding is an extrinsic condition. You need to check that the Laplacian of the coordinate functions are eigenfunctions of the Laplacian. And being isometric here is in the Riemannian sense, and it's an intrinsic condition. A consequence of this is that since everything is explicit, you can just check that if you compute the energy of this map on any fundamental domain, you get a specific number, which is just going to be the rescaled hyperbolic area of your surface, which explains this particular number here. All right, so that's, I think, a lot of content. Is there any question on everything? So here, what we did is we made the link between pure representation theory of Lie groups, of this particular Lie group, with something very geometric and concrete that we can use later. Yeah.
So if you use other unitary representations, it fails?
So no, everything is the same.
The minimal embedding, is it really special for this particular?
So there are a few questions here. So one question is, if you give me any other unitary representation, is there an equivalent minimal surface, say, in that? And the answer is no. The answer is no. For example, if you give me the regular representation, there's no minimal surface that's, there's no area minimizing surface that's equivalent with respect to the regular representation. So this is very counterintuitive, and this has to do with the fact that we're in infinite dimension. Remember, in finite dimension, just by Shen-Yao and standard theory, you can always, by compactness, get some limit, and it's either harmonic or minimal. In infinite dimension, the new phenomenon that can appear is, let's say you have a surface, you want to minimize its area or its energy, and along the sequence, the surface is going to escape at infinity, just because you have a lot of room in infinite dimension. So even though, for example, the regular representation is weakly equivalent to this, there are still very different, different representations. One admits equivalent area minimizing surfaces, the other one does not. Right. That's a strange point.
By the way, popular part B, could row B be replaced to row 0?
Yeah, actually, yes. So this map is actually equivalent by the whole Lie group. Thank you. It's because it's an orbit.
Yeah, the equivalence over there, so if my surface has puncture, the equivalence will make this into a finite area instead of infinite area surface.
You're always looking at the universal cover. So even if you have punctures, in the universal cover, you don't see that. You just have the hyperbolic disk with some action.
But then you say it's Fuxian, so I just wonder whether it's forced to have finite area. Will you?
No, it's not forced to have that, yes. Let's see, what can I say? Because I want to talk about strong convergence, so let me say that maybe you've seen, okay, probably you're much more familiar with Patterson-Sullivan measures and things like this. So Patterson-Sullivan measures are obtained as limits of measures that you get essentially by taking uniform measures on bigger and bigger balls. And then you take the limit, you get some measure on the boundary of your hyperbolic plane. So if you know about this, then actually you know essentially how to prove that this representation is weakly equivalent to the regular representation. So the regular representation, you can think of it also as the space of L2 action on the hyperbolic plane. So the group is going to act on the plane, so it's also going to act on the L2 functions on the plane. This is essentially the regular representation. And this representation, this is a boundary representation that's going to be a kind of limit of such representation where you're looking at functions defined on the boundary instead of inside. But you see that one approximates the other, and the claim is that they're really weakly equivalent. This is the formal statement. And so checking that you have an isometric embedding, this is really due to the symmetries of H. So it's non-trivial, but it's not too surprising. Being minimal also has to do with the fact that everything is explicit, you can check. So what you need to check is this criterion that I described yesterday, I think, which is if you have a map that has value in a unit sphere, you can check that it's a minimal embedding if the Laplacian of the coordinate functions are eigenfunctions with eigenvalue -2 with respect to the pullback metric. And you can check that because you can compute the Laplacian of all those functions. For example, the Laplacian of the Boozman functions are completely known. Yes.
So you were saying just to check for the weak equivalence, you're saying that one checks it explicitly by definition rather than using the norm characterization.
Oh, yeah, in that case, yeah, you can do it explicitly, meaning, let's say, whenever you have a function on the boundary, you can approximate it by functions defined inside in the interior of the hyperbolic plane. And you can see that the action is going to be approximate. It's approximated.
And in this case, I mean, B, when you have this equivariance, is really at BS2R equivariance.
Yes.
And then just whatever lands your group, then
yes.
That's
Is it area minimizing in addition to minimal?
Yes, and that's a very important point. For us, it's going to be true, and it's going to be important, but I'm not going to explain it here, and it's something very, very beautiful due to Besson-Courtegallo. I hope to present the thing tomorrow. Yeah, so minimal is a local condition. You're just a critical point of the area functional. Okay. Yes, if you don't have more questions, I'm going to move on to another thing called strong convergence. And strong convergence is going to describe, as I said, a lot of models of random representations. Strong convergence. Finally, I can give you the definition of strong convergence. So let's say you have a sequence of unitary representations in finite dimension from a finitely generated group. So it strongly converges if, and this is the definition, if you give me a z in C gamma, you have this limit for the operator norms of those elements. So you fix a z, and then for any such z, as j goes to infinity, this norm converges to the corresponding norm, but for the regular representation. Remember, lambda is the regular representation of gamma. And so this notion really came from originally Voiculescu. So Voiculescu in free probability was interested in the asymptotic behavior of a tuple of random, say, unitaries. Let's say you fix an integer k and you fix yourself k random unitary matrices. You let the dimension go to infinity. You want to understand the behavior of this tuple, the interactions between those random matrices as the dimension grows. And he was able to show some interesting behavior, which is that in the limit, what you see is the regular representation in some weak sense. So what he studied was a kind of weak convergence of random representations to the regular representation of your group. For example, the free group. And it's in a weak sense because he was considering not the full spectrum, but he was considering the normalized trace of your matrix. And he was saying, okay, so essentially for any such Z, you look at the normalized trace, and that converges to what you expect to see in the limit because of the regular representation. And that's much weaker. Taking the trace, of course, is you lose a lot of information. That's much weaker than taking the norm. If you can control the norm, you can control the full spectrum, the asymptotic of the full spectrum. So it's much stronger in that sense. And so he had conjectures about such behavior. Was this behavior possible? And Agarup and Thorpe-Bjornson were the first one to establish strong convergence in a specific case. And then later, and more recently, there's been a lot of work on this subject. What I'm going to do is I'm going to give you a few examples of strongly converging sequence of representations. But first, any question on the definition? So this is the strongest way people have to describe the asymptotic behavior of random isometric action on spheres or representations. To give you a feel about that, let me give you some examples where strong convergence holds. So let's consider a non-abelian free group, for example. This is the simplest case. And as a model of random representations, I'm going to use Haar unitaries. So what I mean by that is unitary reps of gamma are in one-to-one correspondence with k tuples of unitary matrices And so if you want to come up with a natural notion of a random representation, it's very easy. So you fix the dimension, and you give me k random unitary matrices picked at random, sampled according to the uniform measure on UN, so the Haar measure on UN. So Haar random unitaries, that gives you some representation from the free group to UN. And the claim is that when n goes to infinity, the sequence of representation of gamma is going to strongly converge. So this is to confirm that in the simplest case possible, indeed, things are nice and have this property. But the good thing about this property is that it holds really in a lot of different settings, and I want to give you another setting where this is true, and it's going to be the end of my talk, which is when, in our specific setting, we are more interested in closed surfaces, so not free groups, surface groups, and let's see. And so here's a procedure that you can do. So let's consider all the homomorphism from gamma to the symmetric group on n elements. So the symmetric group is the permutation group on n elements. And I claim that there's a lot of such homomorphism. It's a little bit harder to see than for the free group, but it's true. And so one idea to cook up a random representation of gamma is to first look at a random homomorphism like that, and then compose with a fixed representation of the symmetric group. So there's a representation that I'm going to call standard that, so this is a group, and that is a unitary representation. N minus 1. So basically by permutation of coordinates. So permutation of coordinates is a unitary transformation, and so that's why there's this natural action of the symmetric group on Cn minus 1. And well, a result which is recent, which is due to Puder, McGee, and Van Handel, is that if you choose uniformly at random, you choose a nu in this finite family of homomorphism, you compose it with the standard representation. The claim is that this, again, strongly converges. And moreover, there's an additional property which is very nice that you do not have if you use random Haar measure, random Haar unitaries, is that the image of gamma by this representation is finite. It's a finite group of unitaries. And so this is useful geometrically because we like to have compact surfaces in the end, et cetera, et cetera. So I can say more, but I'm going to see if there's any questions, and I'm going to stop here, I think, for the content. So thank you.
Is the strong convergence easy to see, for example, in the case of F1?
Yeah, so here I think everything is easy, but as soon as you have two, then it's very, very hard, because once you have two, you have non-commuting elements, and how do you check, like concretely, that those norms converge, right? So what is true right now is that all the known sequences of strongly converging representations are obtained by probabilistic methods, meaning that you do not have any way, say using number theory or whatever, to cook up an explicit sequence of representations having this property. Whereas for weak convergence of Voiculescu, this is very easy. For example, if you have a strongly converging sequence and you take the direct sum with a trivial representation, a one-dimensional trivial representation, so this weakly converges, no problem, but this destroys strong convergence.
Can I replace that standard representation to another ERAP?
Good question. That's a whole subfield of research where they try to extend those kind of things to more general representations of the symmetric group, because you have a lot of other representations. Yeah.
But at least I cannot replace the standard one to say literal permutation of n coordinates.
So this is not exactly permutation by n coordinates.
Yes, well, we're just taking
yeah, you just remove the diagonal.
Then that becomes that.
Right. You want to remove the trivial direction. Thanks.
mentioned like a few people who work on this. Who were they?
Oh, yeah. So So both these people, they have very nice surveys on the whole subject. Yes?
Can you make sure that 1 is not 90 value? Or is it almost surely not 90?
It is almost surely not. Yeah. Yeah.
Other questions for Antoine?
Do you know other equivalent definitions of strong convergence?
This is the only one I know. But I want to say that I made sure to write down this norm characterization for weak equivalence, and I'm going to finish with that. So remember, weak equivalence means the norms are exactly equal. And so what I'm trying to suggest that strong convergence means that the rho j are more and more weakly equivalent with the regular representation. And you can formalize that by saying that if you take any limit representation of those rho j, it's going to be exactly weakly equivalent to the regular representation. And so next time we're going to put everything together. Remember, you have this sequence of representation, sequence of harmonic maps. You take a limit of both. And in the limit, you'll have a weakly equivalent representation to the regular representation and the corresponding harmonic map. And we're going to compare it to the special minimal embedding there. We're going to say, actually, it's equal. So this is how everything is put together.
So up to weak equivalence, there's only one limit point in a sense.
Exactly. So the regular representation is in some sense very stable and the only possible limit up to weak equivalence.
Yes.
Is there a rough formulation of this strong convergence in terms of the C-star algebras of the respective representations?
Certainly, but I know nothing about C-star algebras.
New exercise.
Yeah, I'll leave it as an exercise. Yeah.
More questions?
Yeah.
For this last example into Sn, can you do that with a free group?
Oh yes, also yes. Yes. Whatever you can show for a complicated group, you could have shown it. You can show it for the free group.
All right. Let's thank Antoine again.